So to introduce myself again, if there are new people here, I'm Kai Olav Ellefsen. I'm from the Norwegian University of Science and Technology. And this work was done in cooperation with my supervisor, Keith Down. So for some background. So we've already seen sensitive periods, the concept. And it's, as I explained, it's the concept describes learning that we see in a lot of animals, where they are plastic in some behaviors for a short period of their life, and then they stay stable for the rest of their life to be able to have a benefit of not changing a lot, really, or to avoid the cost of plasticity that we already discussed. And an example of that is what's called filial imprinting, which this picture illustrates. Filial imprinting is something we see in geese and other birds, where they at some point in their life start to recognize their mother, and then they start following their mother their whole life. This is an example of behavior that's plastic for a very short period, and then stays super stable after that. And the benefit of this evolutionary is pretty clear, that it can allow them to identify their mother, but still stay stable in their behavior as they grow up. But it can have some funny effects in that humans can make geese follow them, actually, and they can follow objects, other animals as well, such as this guy. He's even got them to follow in his hang glider. And there's a movie about this guy, if you're interested. There are many other abilities that claim to have sensitive periods, or shown to have sensitive periods. Visual processing is a famous example. Hubel and Wiesel did some Nobel Prize winning work on this, where they sutured one eye of a kitten for various ages throughout its life, and they found that for certain age periods, this suturing would have critical effect. It cannot recover from the change. It cannot follow visual development if you suture the eye at these ages. So their theory was then that there is a sensitive period or critical period for this, and that learning of visual processing has to happen within this period, or not, else it's not going to work. Auditory processing, similarly, is hypothesized to have sensitive periods. Song learning in birds has to happen in a very young age. They learn it from their parents in a young age. They may not be able to learn it as adults. Language in humans is a bit more controversial, but it is indicated that language learning at least is stronger in younger humans. Food preference I mentioned here because it's the domain of these experiments, as the previous experiments. And food preference learning in this case doesn't mean that I prefer pizza to broccoli. It means I perceive broccoli as food, whereas I perceive this glass as not food. And we see in young children, young animals, that they're very experimental in what they perceive as food. They try to eat Lego bricks and all sorts of stuff. But as we grow up, we stop experimenting so much with this. We have a set of things that we perceive as food. So our plasticity on this behavior has stabilized, or our experimentation has stabilized there. And this also has a clear benefit in that it allows us to identify what are good foods as children when we're protected by our parents, and then not experiment too much with it later to avoid poisoning. Now, one thing I want to mention is there's sort of a debate in this field whether to call these sensitive periods or critical periods, and the two names have sort of different associations. The critical periods are typically associated with a period that's very narrow and very sharp and cannot be adjusted, non-flexible. That's how these things were initially proposed. So the initial studies found these to be very sharply defined, whereas a lot of later findings have shown that they are more flexible. They can be extended a bit if stimuli are delayed, and there's maybe some plasticity outside the period as well. So maybe it's rather just a period of increased plasticity rather than the only learning period in life. That's why they're often called sensitive periods now. But I will use the term sensitive period because it's sort of a more general term than a critical period. A critical period is encompassed within a sensitive period. So this is the work I mentioned from Bulinaria. Now the figures are actually my own because I want to publish this online to avoid any copyright problems. But if you look at Bulinaria's figures, they illustrate the same qualitative aspects. So what Bulinaria studied was he had an oculomotor system, that's the system that controls the eye, evolved a neural network for this, and then he evolved an age-dependent learning rate for this system. And he had no explicit costs of learning. So the evolved learning capability is an effect of the costs and benefits of learning, and in this case, the costs are completely implicit. And in his case, they were implicit by having some uncertainties in the system, so that being stable would make you avoid these uncertainties. What he saw was then that individuals would evolve a strategy where they would be very plastic early in life and stay very stable for the rest of their life. Very similar to what we see in sensitive periods in humans and animals. And then another experiment he did was he changed the input-output mapping a bit later in life. Similar, he proposed to giving this oculomotor system glasses at a certain age. And what he found was then that a new sensitive period would be evolved that opened up for learning these changed associations later in life. Finally, one thing that was really interesting and that's been forming the basis of these experiments, he simulated a noisy subsystem. That means he fed his oculomotor system with noise from a certain age, or until a certain age, and after that he gave it the real inputs that it's supposed to learn. And what he found then was that the sensitive periods will be delayed until after the noise is gone, until after there is stable inputs to be able to learn something from. And of course it's pretty clear why this could happen, because when you're just learning from noise, learning has no benefit, it has only a cost, so that evolution would try to minimize learning at this point. And what Bolnaria proposed then was this could maybe model something we see in neural development in brain, where we have multiple subsystems for a given behavior depending on each other, and the higher level systems will then effectively see input as noise until the lower level systems have developed properly. So maybe this can be a way to schedule learning, so that higher level systems are scheduled to learn after lower level systems. And that's what I wanted to investigate. So others have also proposed this. This is by Worker and Thies that proposed this for language development. So language development is known to depend on sort of a hierarchical development of processes. So we have on the low level we learn the phonetic categories, higher levels phonological categories, and so on, up until reading and spelling. And to be able to learn any of these higher levels of behavior, we have to have converged on a good behavior for the lower level ones first. So it's been proposed by Worker and Thies here that sensitive periods could be a way of scheduling this learning, so we ensure that the lower level stuff here is learned properly before the higher levels start to learn. This has also been proposed for other tasks that show this sort of decomposition between lower and higher levels, such as visual processing. So what I wanted to explore then was, if we set up a task that has dependencies like this, where we have lower levels that have to mature before higher levels can start learning or can have stable inputs, will we see these sensitive periods emerge that schedule learning in some way? And then I want to explore what's the effect of this. Can it have the effect of retaining our learning benefits or our learning quality while reducing our learning efforts or our learning costs? Okay, so my experimental setup was a simple food gathering task. This is a bit unclear, but there's two types of food in this environment, really. There's foods and poisons. And we have an agent that we put into this toroidal grid on the top left corner here. And the agent moves around the environment, picking up food and poisons as it likes. And to make things a bit more complex, I placed the foods and poisons inside nuts to increase the task hierarchy a bit. So the agent has to move, study the nut, decide if it wants to open it or not, and look at the food inside, decide if it wants to eat it or not. So it has three decisions. It's the movement decision, should I move forward or turn away? Nut cracking decision, should I open it or not? And the eating decision, should I eat this or not? And then I set up a neural network to make dependencies between these behaviors in the same way that language development, visual development is suggested to have dependencies between lower and higher levels. So I won't go into detail on how this works, but it's based on neuromodulated plasticity. And what it means is that the lowest level of behavior, which is the eating behavior in this case, has to be mature before it can reinforce the learning of the higher level of behavior, which is the nut cracking behavior. So this is similar to the agent opening a nut, saying, I have formed a preference for the food, I think this food is a good one, so I should keep opening this kind of nut. So it has to learn behaviors from the low level to the higher levels to be successful. It's similar to how visual processing, language processing has to form from lower to higher levels to be successful. And I wanted to see then, can these sensitive periods self-emerge to schedule learning here? So if you were at my previous talks, this slide was there. I have to impose an external learning cost here, an explicit learning cost, because the system doesn't have any insecurities, any implicit cost of learning. But these costs of learning are well documented in biology and also in simulated studies. And as we will see, if without these learning costs, learning is just maximized throughout the life of an agent. There's no sensitive periods. So for the results. Without a learning cost, my system is so simple that there is not any implicit cost in learning. So without a learning cost, learning will be maximized. So I forgot actually to mention, the task of evolution in this case is to set the learning rate for each of these three behaviors, and in an age-dependent manner. So it can control the learning rate throughout age for these three behaviors. And it does it in by encoding a delta of the learning rate, really. So it says the learning rate should now increase by this much, and so on. So that's why you see a sort of smoothly rising learning rate here. Without the learning cost, we see learning throughout life. It's sort of just maximized by evolution, because learning only has a benefit. It's beneficial to learn the behavior to be able to eat the foods and avoid the poisons. These plots then show the age of the agent from 0 to 100, where it dies, and the learning rate on the y-axis, and the behaviors from lowest level to higher level. Now, as soon as we impose the learning cost, we see this interesting scheduling effect. And of course, this amount or the size of the learning cost decides how narrow these sensitive periods will be. So we see here that the learning cost reduced the, this is averages over 50 runs, just to mention that. So we see that the learning cost compressed the learning efforts on each level in such a way that things are learned only when they really need to be learned. And this has the effect then of scheduling learning from the lower to the higher levels in a way. So I wanted to explore the scheduling some more to make sure it's really there. So I did what's called a deprivation study. A deprivation study is a typical way of studying sensitive periods, where we take away the relevant stimuli until a certain age, and then we see, can we still form the behavior? If we can't form it after this age, there must have been some sort of a sensitive periods before this that we need for learning. So on the x-axis here we see the deprivation length of the different behaviors, and on the y-axis we see the task performance, which indicates how well it could learn the task of each of the subtasks. And we see that all the subtasks obviously have sensitive periods or even critical periods, because there is a very dramatic decrease around the age of 20 to 40 of task performance. And we also see an indication that the sensitive periods happen earlier in the lowest level of behavior than in the highest level of behavior, in a sort of an ordered fashion. And to make completely sure, I did a statistical test on this to measure the ordering of sensitive periods and comparing their ordering to a random ordering. What are the chances that this ordering would happen by random? And then, of course, I had to find some way of measuring exactly where a sensitive period is, and there's no real consensus on that. What I did was I just measured the center of mass of each of these plasticity graphs. So for these graphs, I measured the center of mass for all my 50 runs. These are averages. And I found that there was significant evidence that the sensitive periods are ordered in this way that I proposed, from lower to higher levels, when we add this cost. Without the cost, of course, there is no ordering. And also, all of the pairwise orderings are as one would expect. Now, to see what is the benefit of this ordering, I tried to shuffle the sensitive periods evolved. So that means I extracted sensitive periods or learning strategies from one behavior, put them into another behavior, and shuffle them around like that to see what it does to fitness. And fitness in this case indicates how well they are able to learn. So what we see, the highest column here is the unshuffled one, and the lowest column is the one where they're shuffled in the completely opposite order. So the learning strategy from foods was inserted into the learning strategies for movement, and oppositely. And we see that the more we shuffle them around, the less well the agent performs, indicating that the more we shuffle them, the more trouble it has learning. So this ordering of sensitive period, in this case, seems to be very important for learning, for correct learning. And finally, I wanted to see what is the effect here with regards to the cost and benefits of learning. So I evolved individuals age-dependently, that we've already seen, that have age-dependent plasticity, and static learners that have just one plasticity level throughout life, but that was also evolved. And then I looked at their fitness both without the external plasticity cost and with the external plasticity cost. And in this case, non-overlapping box notches indicates significantly different needs. So what we see is that the age-dependent and static learners, in other words, the individuals that have sensitive periods and the ones that don't, do not have significantly different fitnesses without the cost. And without the cost, fitness is only based on how well they are able to learn and perform the task. That means that this reduction of plasticity does not lower the actual benefit of learning that they have. They can still learn just as well, even though they reduce their times of being plastic. Whereas with the plasticity cost, we see that there is a big difference between the age-dependent and static learners. The static learners now have a much lower fitness because they have to pay this high cost of being plastic their whole life. This shows then that these sensitive periods, by scheduling learning intelligently, they can retain all the benefits of learning while reducing the cost very much. So to conclude, we see sensitive periods evolve to sequence learning when we have dependencies between behaviors that need to be learned in a certain order. And by doing this, they can minimize learning efforts and retain the quality of learning. Some references, there's more in the paper. That's it, thanks.
Thank you very much.
Yeah. Yeah. Yeah, sorry, that was not really in one of the slides. I may have forgotten this. What I'm evolving is these three things, these three graphs really. So it's the learning rate throughout the ages of individuals. So it's like one number, and then to make evolution's task a bit easier, I said that this lasts for like five ages. Then. Yeah. Yeah.
And I'm wondering if it's possible that basically the system takes some time to neutralize the learning because of the initial configuration of the system when you start the platform. So it takes a bit of time for the learning because the learning rate actually goes down, which creates something failure that actually the learning rate starts at zero. Doing a task, it never needs learning to actually use that task, so you wouldn't use it.
But actually in the encoding, it starts at 0. So it has to explicitly say, I want to go up now to 0.15 to actually start at 0.15. This starts at 0.
So, very quickly, how exactly is the dynamic learning rate encoded? How do you...
Yeah, the encoding. I should maybe have had a slide on this. I think maybe I do. In the additional... Yeah, here. So this is how I encode it. I say we start at 0, at age 0, and then I say for the next 4 learning rates, the next gene decides the learning rate. And it says, for instance, 5 plus 0.5 means it's 0.5 now. And the next one says maybe minus 0.2, that means for the next 4 learning rates, we have 0.5 minus 0.2. And in addition, I evolved it so that it could go below 0, but I cropped the values below 0, because the learning rate below 0 doesn't make any sense. That's how it's able to really shut off learning efficiently at older individuals.
This means that those concepts are the age of agent.
The age, yeah. Mm-hmm.
So that means that in the next generation you can have completely different values for that emitter, isn't it?
For?
In the next generation of the
Yeah.
you can have a completely different value.
For these graphs?
Yeah.
Yeah, they can change a lot. So you have to be a bit careful with how much you mutate things. Because if you mutate things early on here, things can change a lot later. Yeah.
I might have missed something, but you said that there are these 3 actions, and they are sequential, because if you don't move, you get the food, you don't get the food, you get the nuts, if you don't get the nuts, you don't get the... Now, if you don't have to move, choose. Whatever learning rate you have to learn food is available.
Yeah, that's correct.
So, I'm wondering, I mean, obviously there is a kind of progression already inherent to the way you learn because of the opportunity to learn that.
Yeah. Yeah, and one thing I would mention is that when it's born, the agent has weights tuned in a way that is a sort of curiosity. So it always wants to move, always wants to open nuts, always wants to eat things. That's how it initializes its learning. And yeah, you're right. I set it up so that actually learning has to happen in an order to be most efficient. But that is in a way to simulate what we see in the brain, that some learning abilities has to form these more basic concepts before the higher ones can be formed. So that is a design decision I did.
So if you do the numbers at the end, the sequential, well, you got this one task, then the second one different. So it's just the byproduct of the task, rather than results of the costs.
Excuse me, once more.
So because of this progression, you did what you get there.
Yeah.
Because of the way which you design the task, rather than if you don't
yeah, but another thing that we see is that without any cost, it wants to learn everything all the time. It wants to stay open to plasticity all the time. So what this cost does is it makes it beneficial for it to focus its learning in some times, and that it does by the scheduling.
Thank you very much for your wonderful talk. I have one naive question.
Mm-hmm.
Could you tell me why you didn't include the, for example, the network weights and the network topology as heritable weights? Do you have any mind to incorporate them for the?
Yeah, good question. And it's something I considered, but to make things as simple as possible here, I didn't have it. But as you saw in my previous talk, I did have those included. The weights were included, so that I can study the evolution both of weights and of learning rates. But yeah, it could be an interesting extension in this case as well. Mm-hmm.
Yeah, maybe also continuing this question. What about the actual brain that actually has to do this, like in the real brain? It's the brain that's doing the sensitivity periods or something like that. So do you have anything on this or any relation?
To how it happens in the brain?
Yeah, what actually happens.
Yeah, in the brain, well, there are likely, or this has been studied quite a bit, and there's different theories, and probably a lot of them are right for different behaviors and so on. One reason for these sensitive periods in the brain is that an immature brain, or the young brain, has a lot of capabilities that the older one doesn't have. Like it extends axons, it grows and develops a lot more in earlier ages, and that makes it more plastic inherently. But the scheduling effect, of course, can't be explained by that, because the whole brain is developing.
Yeah, my question is about the cost.
Mm-hmm.
I mean, if you just put the cost in the fitness function,
Yeah.
my question is if you have ideas about which would be real cost of learning in real animals.
Yeah, as I mentioned, John Bullinaria's study, he had an implicit cost. And all he needed to do was make the environment uncertain, and learning would actually, no explicit cost, just an uncertain environment, and evolution would select for learning to disappear, because learning from uncertain behaviors make you unstable, so it retains the stability. But there's a lot of studies that have been done on that, and there's I mentioned one reference here that, let's see, did I have it here? No, maybe not this one. But in my other one there was a reference, and there's a whole range of these costs, like the cost of having energy to maintain a brain, doing dangerous exploration of your environment, learning that poisons are bad for you instead of being born with this ability, and so on. A lot of costs are proposed.
Other question? Okay.
Okay, thanks a lot.